Welcome to the third lecture on mass transfer operation. The third lecture will be on the Fick's law of diffusion under steady state and unsteady state conditions. So, before going to the third lecture, let us have a small recap on the last lecture we have. The last lecture was on molecular diffusion. Here we have seen that the molecular diffusion is much slower compared to the eddy diffusion or turbulent diffusion, and we have seen that the effect of barrier on the molecular diffusion is very important. If we put some stagnant layer on the water surface, it reduces the diffusion by around 600 times. Then we have seen the concentration gradient is very important for the mass transfer for a single phase, and in that case the concentrations are defined in various ways. So, we have seen how the concentration is defined in terms of the mass concentration and in terms of the molar concentration. And we have also seen how to calculate these concentrations for a particular system. We have solved few examples on it. Then we have seen the molecular velocities or the diffusion velocities is important for the mass transfer or diffusion. We have seen there are two types of velocities, one is mass average velocities, another one is molar average velocities, and how to define that and how to calculate for a particular systems that we have discussed. We have also discussed the flux X, and we have seen that the flux may be defined with respect to a stationary plane, or with respect to a plane moving with mass average or molar average velocities. So, depending on that, it can be defined as the mass flux or molar flux. Mass flux or molar flux. Then we have seen the relations between the mass average and molar average velocity, and then we had questions and discussion sections at the end. Today we will discuss on the Fick's first law, and Fick's law of molecular diffusion says that flux for a component in an isothermal isobaric binary system is proportional to the concentration gradient a particular direction. So, if we consider diffusion of A in x direction, we can write the flux of A J A x is equal to minus d A B d C A d x, where J is the molar flux of component A in the x direction, C A is the concentration of A and D A B is the diffusion coefficient or diffusivity of component A in B. So, we can relate between flux as per the Fick's law of molecular diffusion. If there are two species A and B and they are diffusing both the ways, in that case we can derive a relation between their mutual diffusivities of component A and B. So, for a binary mixture, if we consider the flux N A, we can write is J plus C A by C into N. And for gas mixtures, we can write C A by C is equal to Y A. So, this is equation 1, and we know that from this we can write N A is equal to J, we know D A B d C A d x plus Y A N. So, this we can again write is equal to minus C d A B d Y A d x plus Y A N. This is equation 2. Similarly, we can write N B is equal to minus C d B A d Y B d x plus Y B into N. N is the total flux. So, if we sum between N A and N B, so N A is this and N B is this. If we sum between N A and N B, so we can write N A plus N B is equal to minus C DAB DYA dx plus YAN minus C DBA DYB dx plus YBN. So, we can write minus C DAB DYA dx minus C DBA DYB dx plus YA plus YB into N. So, this is equation number 4. We know that Na plus Nb is N and Ya plus Yb is equal to 1. So, from this if we differentiate, so it will be dya dx plus dyb dx is equal to 0. So, it will lead to dya dx will be equal to minus dyb dx. Now, if we substitute this Na plus Nb is equal to N over here, and then Ya plus Yb is equal to 1 over here, and dya dx is equal to minus dyb dx. So, it will give you N is equal to minus C D A B dya dx plus C dBA dya dx plus 1 into N. So, this is equation number 5, and in this N will cancelled out, hence we can write this also will cancel out, and we will have D A B is equal to D B A. So, we can prove that the mutual diffusivities between A and B, that is DAB and DBA, are same. So, now we will move to unsteady state diffusion. The unsteady state diffusion, it is defined as the change of concentration of a particular component in the mixture over the time. So, that is unsteady state diffusion. We will try to derive the unsteady state diffusion equation, and which is the Fick's second law of diffusion. Let us consider the control volume and elemental volume, and the balance equations are in plus generation is equal to out plus accumulation. So, mass flow rate of component A mass flow rate of component A in at location M, we can write M A into N A x at x delta y delta z plus N A y at x delta x delta z plus N A z at x delta x delta y. So, this is the mass flow rate of component A in at location x. So, N A x flux in the x direction and N A x at x is equal to value of flux at location x and M A molecular weight of component A. Now, if we do the rate of generation or production of component A by chemical reaction, we can write rate of generation or production. This will be equal to molecular weight into rate of reaction into the control volume delta x delta y delta z. So, R A is equal to rate of reaction and it is the unit will be mole for volume into time. And the rate of mass flow rate out, we can write mass rate of flow out. So, let us say out will be, so at location n, what is the mass flow rate out, that is at distance x plus delta x, y plus delta y and z plus delta z. Similarly, the equations remain similar, but at location n. So, for this control volume, the mass rate out we can write M A into N A x at x plus delta x delta y delta z plus Na y x plus delta x will be delta x delta z plus Na z at x plus delta x will be delta y delta x. So, this is the mass flow rate out, and then another term is the accumulation. So, rate of accumulation, we can write will be equal to delta x delta y delta z, this is the volume, into d rho a dt. So, now if we just write the equation number 1, so equation number 2, this is 3 and this is 4. If we substitute these 4 equations in the balance equations, original balance equation, so we can write the original balance equation was in plus generation is equal to out plus accumulation Now, if we substitute, it will be M A at N A x at x delta y delta z plus N A y at x delta z plus N A z at x delta y. This is mass flow rate in plus generation is M A R A delta x delta y delta z. So, this is generation, and then out will be M A N A x at x plus delta x delta y delta z plus N A y at x plus delta x delta z plus N A z at x plus delta x delta y. So, this is the mass flow rate out plus accumulation. The accumulation term is delta x delta y delta z into del rho A. Rho A is the density of component A del T. So, this is the equation number 5, and if we just rearrange this equation, we can write M A into N A x at x plus delta x minus N A x at x into delta y delta z plus n a y at x plus delta x minus n a y at x into, we can write delta x delta z plus n a z at x plus delta x minus n a z at x multiplied by delta x delta y. So, this is first term, and then we can write plus delta x delta y del z del rho a del t is equal to m a r a delta x delta y delta z. So, this is equation number 6. Now, if we take limit delta x tends to 0, delta y tends to 0 and delta z tends to 0, then divide by delta x, delta y and delta z both sides of the previous equation 6, both sides. Then for component A, we can write m a into del n a x del x plus del n a y del y plus del n a z del z plus del rho a del t is equal to m a r a. So, this is equation number 7.1. So, similarly for component B, we can write m b del n b x del x plus del n b y del y plus del n b z del z plus del rho b del t is equal to m b r b. So, this is equation 7.2. So, if we add equation 7.1 and 7.2, we can write and 7.2, we have del m a n a plus m b n b at x will be del into del x plus del m a n a plus m b n b at y del y plus del m a Na plus MBNB at Z del Z plus del rho A plus rho B del T will be equal to MA RA plus MB RB. We know that rho A plus rho B will be equal to rho, the solution density, and MA RA plus MB RB is equal to 0, because the mass rate of generation of A and B must be equal to 0. So, in that if we substitute these two in this equation, equation number 7.3, we will have del MA NA plus MB NB at x del x plus del MA NA plus MB NB at y del y plus del MA NA plus MB NB at z del z plus del rho del t is equal to 0. So, this is equation number 8. Now, we know that the mass average velocities V x is rho A V A x plus rho B V B x by rho A rho B. So, we can write rho A and rho B, this is equal to rho. So, rho mass average velocity V x will be equal to rho A V A x plus rho B V B x, and rho A we can write M A C A, and then V A x plus M B C B V B x. This will be equal to M A N A x plus M B N B x. N A or N B, these are the molar flux. V x is the mass average velocity, and small v A x is the absolute velocity of component A, absolute velocity of component A. So, then from this we can write del M A N A plus M B N B at x del x will be equal to rho del V x del x plus V x del rho del x. So, this is equation number 9. Now, if we substitute equation 9 in equation 8, the equation rho del V x del x plus del V y del y plus del V z del z plus V x del rho del x plus V y del rho del y plus V z del rho del z plus del rho del t is equal to 0. So, equation number 10. So, this is the continuity equation, or mass balance for total substance. Now, if the solution density rho is constant, if this is constant, so this part will be 0 and this will be 0. In that case, we can write del V x del x plus del V y del y plus del V z del z equal to 0. So, equation number 11. Now, we know that the flux N A x is related with total flux into the mole fraction or mass fraction plus J x. So, if we multiply both sides by molecular weight, we can write M A N A x will be equal to M A N x A plus M A J A x. From this we can write M A C into